At this point, we finally understand how to fully build a convolutional neural network in PyTorch. Now we're ready to outline the upcoming code. As usual, I'm going to repeat the steps of our analysis just to be sure. Step number 1 is to load in the data. For the following examples, we'll be using more difficult datasets, in particular Fashion MNIST and CFAR10. Fashion MNIST was designed to be a drop-in replacement for the MNIST dataset, which today is considered to be too easy for modern machine learning algorithms. One might consider it to be a solved problem. Thus, Fashion MNIST was born, and it was designed to be a standard benchmark just like MNIST, but with the goalpost further ahead. Just like MNIST, it's a dataset of 28 by 28 grayscale images, and it even has the same number of samples. The difference is that instead of simply handwritten digits, we have images of different types of clothing. For example, t-shirts, shoes, pants, and so forth. Your job is to classify these images into the correct category. The CFAR10 dataset is older, but more difficult. This dataset contains color images, so the data takes up more RAM, and the images are also a bit bigger, 32 by 32. It contains classes such as automobile, frog, horse, cat, and dog. You can already imagine that, with such tiny images, it might be very easy to mistake a cat for a dog or a dog for a horse. Step number 2 is to build a model. Luckily, we just discussed that in painstaking detail over the past few lectures. In case you forgot, we'll be using convolutional neural networks. Step number 3 is to train the model. Step number 4 is to evaluate the model. And step number 5 is to use the model to make predictions. Just like the ANN section, nothing here changes. These steps are model agnostic. As per my rule, all machine learning interfaces are the same. One new thing you'll learn about later on in this section is what to do if your dataset is too large to fit into memory, or if you want to augment your data. For example, we know that a dog facing left is a dog, but a dog facing right is also a dog. So should our CNN not be able to recognize both of these orientations as a dog? The answer is yes. We also know that deep learning loves data. The more data, the better. This is why deep learning has come to prominence in recent years. So data augmentation is a method of virtually adding more data without actually having it. We'll discuss this more later on, but for our initial example, we're going to keep things simple. So let's elaborate on step number 1, loading in the data. Luckily, both the datasets we'll be using for these examples are also included in Torch Vision. It's generally going to follow the same pattern as before. You can even probably try to guess the function names, and you might be right. For Fashion MNIST, we load in the data by calling torchvision.datasets.fashionmnist. For CFAR10, we load in the data by calling torchvision.datasets.cfar10. Nothing too surprising there. Inside the training loop, we can loop over the datasets in batches by using the data loader, which, you guessed it, looks exactly the same as before. So what changes? Other than changing the model and changing the data functions, nothing really. So this is a great time to remind you of my 2 rules. All data is the same, and all machine learning interfaces are the same. So just as a quiz, let's think about which of these steps will be the same and which will be different. First, the training loop. As you know, we'll be doing batch gradient descent. Will this be the same or different? The answer is the same. Next question. Let's consider evaluating the accuracy of the model. Will this be the same or different? The answer is the same. Next question. Let's consider plotting the confusion matrix given the model predictions and model targets. Will this be the same or different? The answer is the same. The only minor, non-trivial thing I want to highlight is that the classes are going to be encoded as integers from 0 up to 9 inclusive. But how do we know which integer corresponds to which class? For example, what if 0 is dress and 1 is t-shirt? Is that obvious? Of course not. I just did the easy thing and looked them up on the internet and hard-coded them as strings. This way, when we look at the misclassified samples, it won't say something like 0 is misclassified as 1, which doesn't really mean anything, but rather t-shirt is misclassified as dress shirt, which is more interpretable.